So thank you so much and accommodating my talk here. My name is Castanheira, and I am from the Baylor University, and I'll be talking about today the white dwarfs in the HETDEX survey. This work has been fully funded by NSF. So I'm going to start with this cartoon that we all have seen in textbooks about the acceleration of the expansion of the universe. And might say, well, dark energy is one of the possible ingredients to explain that, if everything else is in agreement with our current knowledge and the best theories that we know. Because we do observe from the supernova type 1a data, this kick on the expansion of the universe. So if, once again, our understanding of the universe is correct, the current universe should have about 75% of dark energy. And this starts to be important, something like around a redshift of 0.4 or about 10 giga-years. And that's it about dark energy. I am going to describe now the experiment that is actually trying to probe dark energy. And we will use, they are using this telescope, which is the Hobby-Eberly telescope at McDonald Observatory. It's in West Texas. And this telescope here has a very unusual and a very unique design. It is actually at a fixed elevation angle of 56 degrees. It's a tilted like an Arecibo design. So basically, my hand would represent the primary mirror. And if you want to point to a certain target, we would rotate the telescope like this. And the reflected light will descend into the secondary mirror. And there is a tracker in the secondary mirror. So we can access our targets for 45 minutes when they are rising, and then for another 45 minutes when they are setting. You might say that's a problem, it's a drawback because we cannot access the whole sky. That's true. But the cost of such a telescope is claimed to be 15 to 20% of the cost of a comparable size telescope. And we can still assess about 81% of the sky. Because of the nature of this telescope and its unique design, it is perfect for Q schedule. So if you apply for time at the HET, you don't go to the observatory and you get your data in the morning, and that's pretty much it. So they observe several programs throughout the night. There are several instruments. They are all spectroscopy for low resolution, high resolution. And this telescope is actually the model for the SALT in South Africa. This diagram here shows basically the idea of the HETDEX with the virus instruments. They actually put the name way before the pandemic, so it's a bit of an unfortunate choice, but it stands for visual replicable unit spectrographs and so on. So that's why it's virus, and everything about the reduction of the data is cure, vaccine, and so on. So it's sorry, I mean, we gotta laugh now, but yeah. Anyways, so this is a diagram of the telescope, and you can see here it's a segmented mirror telescope at a fixed altitude. And the virus spectrographs sit on those cages on the side. And I'm sure you can see that green fiber optic cables that will go to the tracker on the secondary mirror. So one important part that I want to mention is, of course, the size of the telescope or the effective mirror of the telescope is changing as the targets are lower in the sky and rising. So it becomes very tricky to do proper reduction of data and flux calibration as well, because your size of your mirror is going to not be always the same. But we've been able to work some ways around that. So the group that proposed HETDEX is actually targeting Lyman alpha galaxies. This is a spectra of one of those Lyman alpha. They are very, very common. They used 156 virus units covering between 3,500 and 5,500 angstroms. In one shot, we can get about more than 3,400 spectra. It is lowish resolution, about 2 angstroms. And the exposure time for this survey is 18 minutes. So the time that they are being observed is also dark time. So the sample is very, very homogeneous, and the treatment of the data is very homogeneous as well. Here, another thing that has been improved is the field of view of the telescope. So it is about 22 arc minutes nowadays. And this is an actual picture of the telescope. It's a little bit difficult to see, but I mean, the contrast is not great between the dome and the mirror, but this is the mirror. Those are the controllers under the telescope and the cages where the virus spectrograph is. So it's a bit difficult to actually take a full shot with a phone. Another thing, this is fiber fed and IFU. So we actually expose the targets or the field of view that we want in 3 dithers. So we try to fill in all the gaps. So we are pretty confident that we are doing a very good job in terms of getting all the flux from all the sources that we are aiming to observe. And here's oh, I'm so sorry. Did I skip that? I did. No. Dear Lord. Okay. And here's the footprint of the HETDEX fields in galactic latitudes overplot with the Gaia data. And I will talk a little bit about, because this is probably the only, one of the few talks that you see a survey going a little bit deeper than Gaia, so, because our sources are a little bit fainter. In this plot here, I have the signal to noise of the continuous sources. So I want to make a point that everything that has been observed by the survey will be analyzed and the data will be selected and so on, and in the same fashion. So the main group of the HETDEX collaboration is looking for those Lyman emitting galaxies. All the continuous sources for them is trash. Guess what? We are interested in continuous sources, and we will take all the stars that they can give us. This is a plot showing the signal to noise ratio for all the sources, the continuous sources. So the trash of HETDEX, basically, down to a magnitude of 23, I think, in this case here, in G. And this is one of my favorite plots that we have the stars that have been observed for the data release 2 from HETDEX. And right here, we have all those sources colored, and we kind of add them and average them out. And in this plot, I show here displaced by flux on average. So all the way up there in blue, we can see the white dwarfs. We see a lot of other A stars, F stars, and so on in the data as well. So what do we do with all the sources that we are finding in HETDEX? We get the spectra and we fit the data. So to fit the data, we worked in collaboration with Detlef Kuster, and he actually fit the data for us. So that is the top fit of one of the white dwarfs. And he also used the colors from Gaia and the distances, if we had any information about that. We decided to use a slightly different approach and to select the targets and use the distance in order to use the distance and then use the size of the stars to calculate the absolute flux that we would be getting for the models if we place the models at the distance that the stars are. This is not a novel strategy or novel technique, but for a telescope that is actually changing its size as the observations are happening, we are trying to make sure that we are doing a good job in terms of the flux calibration. And I'm not sure you can see the numbers here, but especially the bottom one, you cannot see very well. But the top one, the temperature is 17,500 and something Kelvin, and the bottom one is 17,250 Kelvin. So getting a difference in uncertainty of 250 Kelvin for a telescope that is changing size is a completely different approach in terms of the way we are fitting the data. I think it's pretty successful as a first look of what we are seeing. The log G is also a difference of 0.25 index. The top one is 8.25 and the bottom one is 8. So we're still pretty, thank you. We're still pretty confident about that. And if you haven't looked, this is a trash spectra with a G magnitude of almost 20. So I think this is pretty remarkable and pretty impressive what we are getting. I want to talk a little bit about the calibration in the UV, or as low as we can see here in the cutoff of the atmosphere. This curve here represents the relative throughput for HETDEX, and this is what they have been using for all the sources, and they have their calibrating stars as they are taking the observations. In this plot here, I show the comparison in black from the data that we obtained with HETDEX, and in red from Sloan. Now, as you can see, the UV part, which we're multiplying by over 100 here, or nearly 100 times, is we don't have any other comparison. So we actually did some analysis from all the white dwarfs in the data release 3, and we saw this little hump going on here. And we actually used, in turn, the white dwarf stars to recalibrate the whole survey. So I think that our contribution is not only, hey, let's take a look at the trash that you don't want to use for anything else, but let me use the white dwarfs and the models of white dwarfs and all the information that we have to white dwarfs to improve the results that will come out of this survey. So this is one of the, I think, the most remarkable results that I can share with you. The paper is, we are writing it down now, and always next semester will be better, right? So anyways, we predict to find in this survey about 2,000 white dwarfs. We do have a problem. I mean, not a problem, it's not a bad problem, but we will be looking at stars that are very faint. So we're going down to magnitude 23. So it will be very interesting to analyze those fainter targets that could be probing a different population, stellar population. One thing that I also want to mention is this sample is limited by magnitude only because we don't have any selection effects like this Lone Digital Sky survey had. And we also have more data from the parallel survey, which means every time that HET is taking data for planet search from galaxies, you know, supernova, whatever, the other fibers that are available in the field of view are being being fed into the virus spectrograph. So we get way more data. This parallel data is not homogeneous, obviously, but it's still data, and we can still visit some of those fields over and over again, especially, for instance, planet search fields that they are visiting all the time. Every month they look at the same objects and so on. So it's a very interesting and powerful survey. And of course, if we see some interesting targets, we can always apply for time with HETDEX and get that observed a little bit longer and so forth. And finally, I just want to invite everybody because in 2024, there will be a total solar eclipse, and Baylor University is in prime real estate for that. And we established some collaborations with Lowell Observatory, Discovery Channel, and the city of Waco. So we're going to have a tiny conference, a 2-day conference, if you need a reason to go. Just before I think about it, will be physics, astrophysics, whatever we want to do. Sorry, sorry. Talk to me if you're interested in, yeah, and book your hotel because they're already there. So yeah, let me know. But yeah, we're excited, and hopefully we're going to see lots of you coming up there. So we have some fun activities. Well, thank you.
Question for Barbara. Okay, that one here.
Thank you. Very, very nice talk, Barbara. I'm curious, I've got a couple of really short questions. What kind of radial velocity precision can you get for these white dwarfs?
That's a very good question.
Thank
I haven't
you.
looked at that. I haven't looked at that, but yeah, the resolution is very low. So we have 2 angstroms. So
okay, and are any of these fields revisited?
yes, yes. Some of those stars we have 3 to 4 spectra because they try to get deeper and deeper. Yes, so that's right now as of the DR3, but we probably go back them every year.
And finally, I think the number of white dwarfs you're finding was like 2,000, but I remember when I was a grad student, I think there was thought to be a lot more. Is that because of the delays of HETDEX have revised the sample, or why? I mean, down to that limiting magnitude, there's like 100,000 in that part of the sky.
So no, and yes, a little bit, but no, the number, if we include the parallel survey, we get something like 10,000 based on historical observations. I mean, the history of observations at the HET, we estimated up to 10,000, but 2,000, we are confident that will come from the main survey, and that's going to be homogeneous data, or very same exposure time, lunar time, and so on. Yeah.
Thank you.
Boris?
Have you seen any exciting non-DA something weird on your spectra?
No, not yet. Short answer, not yet. We have looked at the subdwarfs, and yes, so with Stefan Geyer, we were looking into some of those. So yes, we've been looking for other stars as well, but no, I haven't found any exotic white dwarfs.
And what's the total area of the survey?
It's 18 square degrees or 10. I have to look. I don't wanna say the number. It's gonna be wrong if I say it, but sorry, but I will look it up.
Can you go back a few slides when you were showing the how you were recalibrating? Yeah, here. Yeah. Like that. So you're scaling the white dwarfs model to the distance given by Gaia and recalibrating the spectrum based on that.
Yes.
And particularly you're seeing now this effect in the UV. What's going on between H beta and H gamma there? Is that instrumental?
Yes, there is a discontinuity in the detectors. Yes. So we are also going to look into that. But it is yes. That was one thing that, yes, we learned about that as well. We confirmed that as well. So we might have some issues for us because, again, the instruments were designed for detecting the Lyman alpha galaxy. So there is one part that both detectors meet. So
thanks.
Sorry.
A basic question. I'm just curious, how are these continuous sources selected? Just magnitude limited, that's it?
That's it. Magnitude limits, whatever does not have any emission line, they put into a file and they send it to the stellar working group, which it's us. So.
No more questions? Let's thank Barbara again.
Thank you.